All right, so thank you for being here on time. We have just 50 minutes today, so we are going to be trying to squeeze as much as I can without running too much. So there's going to be like a small agreement between me and you every time we start class. So the agreement is the following. I'm here for trying to communicate to you, right? So I'm here because I'd like to send a message across. Every time you don't have idea what's going on, you think I'm confusing, you cannot understand my English, you know, I have a very strong Italian accent, you know, mamma mia. No, okay. Yeah, I make jokes, so don't take every word I say as truthful. If I'm talking about, you know, being aggressive or whatever, I'm joking, most likely. If I'm talking about, you know, deep networks and stuff, usually it's reliable. Yeah. Okay, so the point is going to be like, every time you have no idea what's going on, just stop me, call me Alf. I have no whatever idea what's going on here. Stop, repeat, explain to me again. I will explain to you as many times as it's required. If you do not understand something, it's almost 99.9% my fault, because I haven't taken into account your background, and you know, I'm skipping some steps, perhaps because I'm not used to you know, maybe this class or your background or whatsoever. So again, I'm here in order to educate, in order to communicate, and I can't do that if you don't help me, right? So if I ask a question, you understand what I'm saying, you should like nod your head, because if you're like yeah, not reacting to my jokes or questions, then I have some issues understanding whether you are making any sense of what I'm saying. If you get distracted, I will try to, usually I throw chalks, but we don't have chalks here, right? I think I can try with markers, but maybe not, right? Just for undergraduates. You're grown-ups, so you should be able to, you know, keep yourself awake for the next 45 minutes, more or less. Do not turn off, because if you turn off, I can't come there and take you and shake you, right? Again, you're not undergraduates anymore. You're grown-ups. Oh, some of you are undergraduates, I guess. So, okay, I figure out where you are, so I may come and shake you up. But for the others, you should be able to stay awake for the next 50 minutes. I know it's late night, so try not to eat before class, so you don't have like you know, the after dinner thingy, whatever. So yeah, so don't take me too seriously. I'm Italian, right? So inspirational. Like, why are we here? To take a A, maybe. So it's a competitive class, right? At the end, we're gonna have a competition. Don't get too scared. We do not only like consider how you're doing well in the final ranking. We also consider how well is your work, right? So sometimes things don't quite work, but you still apply yourself. So that's actually what matters. Nevertheless, if you actually win the challenge, you may have some gifts and presents and something from us. Yep, that should be it. Also, if you take a very nice grade, you may come and you know, join the lab, perhaps, with Jan and so on next semester. So just saying, you know, take a nice grade so you can serve later as well. Okay? All right, kind of joking. So neural networks, right? Did we see yesterday, what neural networks are? Kind of, no? So I think we mentioned a few applications. One of those were classifications. So let me just give you a small recap about what classification is. So what classification? Let's say I take a picture of something, right? Let's say I take a picture. It's a 1 megapixel camera. So how many dimensions will be my image? So if I take an image, I can consider my image, which is going to have RGB plane. And it's going to be having like 1,000 pixels in the vertical and 1,000 pixels horizontally. So you're going to have overall 1 million pixels, so 1 megapixel. You have RGB, so how many pixels, how many values will you have? 3 million, right? Okay, cool. So you can think about this image, which can be thought as this kind of stack of 3 layers, as one point living in this 3 million dimensional space. And this 3 million dimensional space is really, 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 really large, right? You can move around and nothing happens, right? So let's say I take a picture of a dog, and I have here a picture of a dog. Let's say I take a picture of a cat. Where is going to be a picture of a cat? Here, here, or here? Sorry. Okay, hands up for who thinks if this is my cat or dog, who thinks the cat, the other one, is here? Okay, maybe you were actually paying attention yesterday. Who thinks the other point is going to be here? Okay, who thinks the other point is going to be here? Fantastic. Okay, so you're actually on the right thing. So everything is just in the same damn little spot in the space, okay? And everything that actually makes sense is here. Everything else is just trash. And so we have to take the space, go here, take this point and move it here. How do you move points? Have you taken linear algebra? Yes? No? Okay, about linear algebra. So, as you may know, or if you don't now, you do, I do have Twitter, and I'm a very annoying person on Twitter because I talk a lot. So let's see Twitter. Okay, open Twitter. All right, so here, I cannot zoom. So twitter.com, right? So then you go, oh, there's no internet, see? Ha. Oh, let's connect, Wi-Fi. Yes, I'm connecting. All right, almost there. Okay, so you want to do a search, and you do linear algebra. I cannot see anything here. Okay, damn. Okay, let me zoom here. Okay, so you go on top right, there is the search, you do linear algebra, then you do parentheses from me, alf, c, and z, okay? So here's how you find out what are the questions for the midterm, right? Just check on Twitter. I usually, leak stuff there. All right, so here you have this, actually it's very nice, this book, Introduction to Linear Algebra by Gilbert Strang. So you may want to, look up this stuff, but the other one is this one here. So you'd like to check the third tweet here, where I show you the essence of linear algebra by Grant. Maybe you know this guy, Grant Sanders. If you don't know, well, you should know now. Just check this link, right? And this link is going to show you how you move stuff around, okay? Anyhow, that was the first link for today. So how do you move things around in a space? For the one actually that know how linear algebra works. You just talk, you don't raise hands.
Multiply by matrix.
Okay, matrix multiplication, what does it do? Rotation. I can't hear. Okay, first, matrix multiplication is a, what kind of operation? Linear transformation. Okay, what are the linear transformation? 1, rotation. 2.
Translation.
You sure?
Stretching.
Stretching, okay, fantastic. Then third. Stretching, scaling, I guess, let's say scaling, stretching is number 2. Then, if the determinant is negative, what do you have? What is it? Reflection. Third one, then one more. Is it?
0.
Okay, I guess we have 3 for the moment. There should be one more. Hold on. So scaling, right? So you have scaling this way, you have scaling in that way. Then you have rotation. Then you have reflection. When you have reflection? Identity. No. Identity does nothing, right? So, okay, rotation means the matrix is orthonormal, right? Cool. Second one, you have scaling. When do you have scaling? Okay. Well, okay, we're shearing. Fantastic. So we have the 4, right? So we have rotation, we have zooming this way, you have shearing, right? And then you have the reflection whenever you have the negative determinant. Cool. Still, I wanted to move things around. Is motion, translation, is it a linear operation? No? Yes? You can answer. You don't have to raise hands. Adding scalars. Is adding scalar a linear operation? Not sure. Because 0, where is the 0 mapped to, right? Only if the 0 is mapped to 0, then you have a linear transformation. Anyhow, so you have translation, which is the the fifth operation, if you use affine transformations. So all those nice things, you're going to find them there, okay? So check those things are very useful. Anyhow, so finally we figure out that if I have everything up here, we have cats, hippopotamus, dogs, and whatever, I want to take them down, I want to translate, right? Yes, talk to me. No, you don't talk yet, okay. All right, so we want to use translation. And then you translate this stuff in the 0, so you have all the things here. And then how do you separate those things apart? So all of them are all together. How can I... So we mentioned what are the four different transformations that a linear transformation does. Scaling, right? How do you scale things? With a diagonal matrix. Fantastic, cool. All right, so fantastic. So how do we diagonalize matrices? That is the second question. You can figure out if you check Twitter. So we open a new page. We go Twitter again. We go on top right. You should take a note about how to do this stuff. You do SVD parentheses from alpha CNZ. Okay, cool. Then if you go here, it's like SVD. So this is from also Gilbert, right? So you also would like to check this one. If you click here, it's going to be more information about midterm, right? Last year. Okay. You know too much now. Okay, anyhow, so you want to check this stuff out. Anyhow, we have figured out that by using matrices and scalars, you can move things around, and then you can zoom, right? And so again, I have things all collapsed here. I can't do anything, so I take it down with a translation, right? Yes, no, do like that with your head? No. You following there? Yes, no, okay. It's boring? No. Okay. All right, so you take this one, you put it down with translation, and then you zoom it, right, with a matrix, perhaps, diagonal with some singular values, right? Cool. And then what? So I have this thing zoomed up. So classification, what is it? How do you perform classification now?
Assign labels to your points.
You'd like to assign labels, but how do you do that? So whatever you would like to do is going to be basically moving these points in different regions, and then you slice them, okay? And so this is going to be part of the next class. Right now I'm just showing you how a neural network does this. I hope you're going to be enjoying this video. If I find my cursor. Okay. All right, so we start from here. Full screen, perhaps. All right. So can you see anything? No. How do you turn off the lights? Can someone figure out how to... Oh, maybe here. Yes? No? Good night? No, hold on. All right, good night. So at least this one, then I turn it back. So here we start with these 5 branches of a spiral. And you can see that each point is going to be basically represented as what? How can you represent each of those points without a color? Okay, where do these points live? On a 2D plane, right? So this is a 2D plane, this screen here. So each of those points is represented as a tuple, right? That is representing the x and the y coordinate. Then the color there represents a third dimension where it's going to be basically representing the class to which each of those points belong. And here we have 5 different branches of a spiral. So this is the input to my network. It's going to be a bunch of points without colors. And then I ask my network to separate the points by color. Okay, is it clear what is the task I ask my network? You cannot raise your hands because I cannot see shit, right? So, so you had to shout back because I don't see you. You understand, right? What's going on here right now? So we start with this guy here, which is just 5 branches of a spiral. The network doesn't see the colors right now, and the network will try to separate the colors apart. So this is what my network does. It takes the space, the space fabric, and it performs like a stretching of the space fabric, right? How cool does that sound? And you should do like, oh. Oh, see? Okay. We had to do multiple iterations, I think, here. This is your first class. It's okay to be shy. All right, so this is my network, which is basically stretching the space fabric in order to get all those points that are belonging to the same color, to the same class, to be in the same subspace of this final manifold, such that once we reach convergence, or whenever we reach at the end of this animation, you have all your points that belongs to different spirals linearly separable. And so now you can just use logistic regression, right? Or like one versus all, whatever regression is called. Yeah, I don't know. So, and in this case, the last matrix is represented by that 5 arrows there. So those 5 arrows represent a matrix, which is how many rows, how many columns. So what is my output dimension here of this network? What are we trying to infer in this case? The classes. How many classes do we have? 5. So the number of rows of this matrix will be 5, right? Because the height of the matrix is the same dimension where you're shooting to. And the width of the matrix represents the space where you're shooting from, right? And so what's going to be my width of this matrix? 2, right? So this matrix is going to be a 5 times 2 because we are shooting towards 5 dimensions, the 5 colors over here, and then we have two columns, right? So it's going to be basically the 2 coordinates of the tip of the arrow. And those arrows are just centered in 0. We're going to talk more about that intersection, I guess, in later lessons, if I actually manage to make a video about that. But can you see that kind of cute intersection at the center? Have you ever seen that kind of intersection before? Have you ever taken a bath? I mean, yeah, bubbles, right? So whenever you have multiple bubbles touching together, it looks like similar to that, perhaps. Maybe not, but I don't know. It looks to me. All right, so that was the first network, okay? And this is how these networks work. These networks basically take the space fabric and then apply some kind of transformation, which is still parameterized by matrices. So I have many, many matrices, and then I have nonlinearities. Why do I need many matrices, or why do I need nonlinearities? Can I turn on the light, or you still like to watch? Okay. Yeah, otherwise start sleeping. All right. So here, basically, this guy here is going to be a network with 2 matrices. My first matrix maps my input, which is living in which space? 2 dimensions to an intermediate layer of 100 dimensions. So my network architecture is the following. So I have my 2 neurons here. I map this one to 1, 2, 3, so on here. I have 100. Then I have some nonlinearity, which is going to be just the positive part. And then from this guy here, I do something cute or funny or weird, I don't know, depends. So from here I map down to, okay, what should I do after? Let's say this is my network. What's going to be the last layer of this network? 5, right? But how many dimensions has this screen? So how can I plot there? I don't say PCA. So I do this one. Okay? Such that I can show you there the linear interpolation between this point here, which I call embedding in this case, but just a way I call this stuff right now. And my input. Okay? All right, that's pretty much it. So this is my neural network. Has one input layer, one hidden layer, one kind of embedding layer which does nothing, and a output layer. Okay, so it has one hidden, and overall I count this as 3-layer neural network because it is 1, 2, and then this stuff is linear, right? So why do we need nonlinearities?
Because otherwise it will be similar to having just one layer in the network.
And what can one layer, okay, so he said without nonlinearity it would look like a single layer neural network. And a single layer neural network, what can it do?
Just scaling.
Scaling, translation, rotation, reflection, and I guess shearing, right? Okay. So guess what's going to be the next part of this class? Let's check how one network with one layer works, okay? Questions so far? Also there in the, yeah.
What do you need embedding again?
For just displaying stuff on the screen. More questions. Again, don't raise hands. You can just talk to me. Can you hear me over there? Is everything okay? Awesome. All right. Thank you for approval.
So by saying displaying on the screen, what are you exactly displaying? I don't get it.
So these 2 points here represent the coordinates of my input points, right? So this is going to be my x coordinate, my y coordinate of the input space. This one is going to be my x coordinate and my y coordinate of this embedding space, which is linearly separable, given that I have, obtained 100% accuracy with the training. We haven't talked about training yet, but does it make any sense? The answer, what I give you? Okay. Yeah.
What if the two embedding layers were kind of in between, more hidden layers? Would that matter at all?
So this is just a way to visualize 5 dimensions in 2 dimensions. Instead of doing a PCA, I just do a PCA. Hold on, he hasn't finished.
I was just curious, why you put it right before the output.
Because I'd like to see what the network output looks like in 2 dimensions. Okay, right.
But will this not shrink the information that goes to the last layer?
Why is that true or why is that false? You'll see that next time. It doesn't shrink because, again, those two, you can still multiply them together, right? It looks like one single matrix. And actually, this works better. More about this later on in the class. Actually, Jan is going to be touching about this. Okay, we still have some time. All right, so how did I make these animations? First option, I'm a magician. Why you're laughing? It's actually true. But anyhow, I know how to use Matplotlib. I've taken this class 3 times, and I never pass it. Okay, all of these are free. All the three are true. I never taken the class, but okay. I've been on the other side. Yeah, so this is not magic, right? So this is just visualization using Matplotlib, free open source code, and PyTorch, which is going to be our library, which we're going to be using for the writing these models. So it's very, very convenient. Was made by a student of mine back, I guess, in 2016. So, be that cool. No, I'm just kidding. You can be even more cool. All right. More questions? No, okay. So now we actually can go to the more concrete part, right? So this was kind of abstract. I gave you some interesting, delicious, I guess, appetizer. Let's get on the main course and let's see how you can actually get started, okay? So everything you're going to be seeing in my classes are in my GitHub repository, which you are going to be forced to star. No, I'm just kidding. But if you don't star it, I will take notice. All right. github.com/@cold. So @cold stays for something weird. So my Italian name is Alfredo. Fredo can mean cold, and al can mean at. So that @cold is going to be the kind of transliteration of my name. So @cold, you go there. Yeah, that's me. How cute. The first one with 1,300 stars, and I guess you have 200, so it should be 1,500 by tonight. It's going to be the class repository for the class, right? And so we're going to be, if you don't have, so you should have like a Unix. Actually, no. PyTorch works also on Windows. I don't use Windows, so I have no idea. But if you have a Mac or a Linux machine, everything works just fine. If you have a Windows, it should work as well. I haven't tried. So how do you access this stuff? You go there. Here you're going to have the page website as soon as we actually make it. We are going to be actually looking at the repo, the notebook number 2 right now. If we have time left, we can also check a bit of a more basic introduction to the tensor tutorial. How many of you have no idea what NumPy or NumPy or whatever you want to call it is? Hands up. Don't be shy. So I changed my question now. Does everyone here in class know about NumPy and has it used before? Are you going to be shaking your hand? Just shake your head, right? So who has no whatsoever idea what NumPy is and how it works and never used Python before? You know, it happened, don't laugh. Okay, because if you don't know about that, there is also the 00 class where you implement things from scratch, but I guess that's too much back. So I guess the number 1, it perhaps is not too worthy going over. We see if we have some time left. It basically gives you some introduction about how to use basic PyTorch routines for creating tensors, which are basically multi-dimensional arrays in NumPy. And so it creates tensors, it multiplies tensors, it just initializes, creates random stuff. So it's not that different from NumPy. Again, we can check them out. We can check these out if we have some time afterwards. Otherwise, it's going to be like left as an assignment to go over this. It should be a very easy, gentle introduction to how to get started with the API, okay? Complaints about this? No? Wow. Or you're shy, or you're too nice. Okay. You're not laughing. That's okay. All right. So, okay, I'm joking, but you're not getting the jokes. It's fine. One more advertisement is Typora. This Typora thing, I love it so much. It's a markdown editor where you can write down your notes in LaTeX and markdown, right? So you can write, for example, whatever soft argmax, which is something you're going to be learning about, which I call it this way. So you can use LaTeX in a markdown file. It looks very good. For example, here I annotate articles I read. Okay, so this is called Typora, Typora. Okay, that's just promotional message. I don't get paid, so it's free too. Okay, all right. So how do we get started there? We open the terminal with zoom such that you can see something. So we can go, for example, inside. Oh, this is going to be different. Let's say we go inside that inside that repository. I go somewhere else, which is going to be my notebooks, and then my video lessons. Okay, so you're going to be basically running conda activate deep learning mini course, and everything just works if you have installed and you have followed the instructions in the README. Okay, so right now, if you just type IPython with Python 3.7.6 will open. You can do import torch, for example, just to see whether everything works, and then you can type, for example, torch.rand and 5. And this one is going to be creating a tensor with 5 numbers, which are randomly picked from a 0 to 1 uniform distribution. Okay, so this is just to check that everything just works fine. If this works, then we can actually start and play with the notebooks. You're not you can try to follow along in class with the computer, but I think it's better for you to actually follow and what I do here. I'm a clown. I try to engage with you. If you isolate yourself with the computer, maybe sometimes you may lose some of the nuggets I give you. Anyhow, so it looks like everything works here. So I'm going to be just opening the Jupyter Notebook. And things are black, because I like them this way. Yeah, black is good. All right, so we're going to see this random projection to be starting. Yeah. Let me go full screen. You should be complaining if you don't see things, right? I kind of know what you see, what you don't know, what you see, what you don't see. But if you provide feedback live, like, I can't read anything, or can you turn off the lights, that would be also useful, okay? So do interrupt me, do talk to me. Can you see? Is it okay? Yes, no. Thank you. All right, let me turn off that one too. All right, okay. So what I do here, I'm gonna just import some utilities I define for plotting stuff. Then here I just import Torch, and then from Torch I import this NN library, which is simply, I'm going to be importing the matrix multiplication and the addition of a vector, okay? So matrix multiplication is going to be a linear operation, plus the bias, plus the translation, we have the affine transformation, which is the one we were talking about with the 5 different transformations. And then we're going to be importing, I guess, some linear function somewhere. Moreover, I import from Matplotlib those things for plotting things. I also import NumPy as NP. NumPy, I don't know. Is it NumPy, number, or NumPy with numeric? People complain about that. I don't know. Anyhow, so I use some default things. And OK, this is the first line, torch-specific line. So this is going to be device equal torch dot device CUDA 0 if CUDA is available. Otherwise, CPU. What is this? If I am running these examples on a machine which has a GPU, automatically Torch will run on the GPU memory, right? So your machine has a CPU which makes only sequential operations, one after each other. Might be very, very, very fast, but it's still sequential, right? It's like your brain. You can only do one thing at a time. If you try to drive and smoke and take a phone call, yeah, you might not be here tomorrow. So you can only do one thing at a time, right? And that's like the CPU of a computer. And then you have some local memory, which is the main memory is called RAM, random access memory. On the other side, if you would like to speed up things, you can use something that is much slower, which is called GPU. So why would you use a GPU, which is slower than a CPU, to speed up your computations? Because although it's very, very much slower, it can perform many, many, many more computation at the same time, right? So if the CPU is going to be like running very quickly from one side to the other, it's going to be beating your GPU so many times. But the GPU does. Okay. All right, so the GPU will have a memory, which is called device memory, which lives on the GPU. I think right now they are planning to get some access to the main memory of the CPU from the GPU. I think they are working on that. I don't think it's yet out. Anyhow, if you work on the GPU, you will have to create your tensors in the GPU memory. But you don't have to worry about that. As long as you specify that thing over there at the beginning of your code, PyTorch will take care and will put your tensors in the right location for you. If you're going to be using a TPU, a tensor processing unit from Google, similarly, you're going to have PyTorch putting your tensors in the TPU memory, which is close to the actual processing unit there, which is going to make your operation, computed in a faster way. So this is a stupid single line, but it's important, okay? Again, about the PyTorch stuff, you won't be tested in the midterm. Midterm is going to be mostly about math. This stuff is going to be essential for actually managing to succeed in the final project, okay? So if you are trying to beat others while using CPUs and they are using GPUs, good luck, okay? And yeah, I'm ironic, but people tried and then complain, and then I don't want complaints. Okay. All right, so here we create 1,000 points, and actually I do this one, okay? So 1_000 is the same as 1,000, but it's better to read. And so here I have 1,000 points, and my X, capital X, is going to be my design matrix. It's going to be having 1,000 rows and 2 columns, okay? And it's sampled from a random N distribution. So if you go here, you press Shift Tab, you're going to be having this thing opening up. And you can click here, you're going to see what is this stuff, right? So rand N is going to be return a tensor filled with random numbers from a normal distribution with mean 0 and variance 1, also called the standard normal distribution, okay? So how did I open the help? Do you know this stuff? Have you ever used notebooks before? Is the first time you saw this help? Some of you may have seen this the first time. Okay. So how are these capital X going to be looking like? How are these set of points? What is your expectation for this set of points? You're supposed to interact?
Small values near to 0.
Small values near to 0. Okay. So you're going to have a cloud of points. What is going to be the radius of your cloud?
You mean the standard deviation, right?
Say again?
You mean the standard deviation?
No. I'm just speaking, since I don't like distributions, I'm going to have like a bunch of points, which are going to be basically somehow circularly distributed. I'd like to know what is the average radius of this blob. A half? Who offers more or less? 0. Average. So you have the expectation of the square of the x square, right? Square root of the expectation, well, whatever, like expectation of the square root of the sum of the squares, right? Okay, someone said 1/2. Who wants more? Who beats more?
That or 1.
Say again?
It's that or 1.
That or 1. So you have the standard deviation is going to be 1. So are you going to get points outside the standard deviation or not? You know the bell curve, right? Yes. Where is the 1 standard deviation? Close to the center, far away? How much larger than the standard deviation is the bell?
67% is 1.
Oh, okay, roughly. Try to guess. Just shoot numbers. It's okay. I don't judge you yet. No, you're too shy. Okay. Where's my student? Answer. Okay, fine. Yeah, fine, not fine. Okay. There we go. What is this stuff? It's cute, I know. Can you see anything? Should I lower it? Okay, I just lowered the light, whatever. People with the recording are going to be complaining, but. Oh, okay, still, I don't know how to turn off the first thing, so you get dark. So, what are those red and green arrows there? Okay, you can guess, right? I don't bite you. The axis, fantastic. Which axis? What is the length of those things? Come on. Unit, right? So those are the unit vectors. Why one is red, why the other is green?
Visual clarity.
Okay, fantastic. Which one is X? Which one is Y? X is the red one. Why is that? Because you have RGB, right? Because you have taken some graphic class before this. So R is going to be always, red is going to be always the x-axis, green is going to be always the y-axis. Those are unit vectors, and therefore this cloud of points spans roughly. What is the average radius here? Can you guess? More or less? 3. Fantastic. That was the answer. Okay, so you have a cloud of points roughly large 3, right? Uniformly, like circularly distributed, right? Sort of. All right, cool. So we're going to run now.
Sorry, I didn't get how is the range equal to 3?
You can try to put like this arrow here, one more arrow here, One more arrow here, you have 3 arrows there, okay? More or less. I'm a physicist, right? Yeah. Later I will be a mathematician. Okay, now I'm a mathematician. So visualizing linear transformations. See, here I compute the SVD, singular value of decomposition. Again, there is the video I pointed out before. So I'm going to be multiplying this cloud of point by a matrix. So what does a matrix do to this circular blob? Come on, you know this stuff. You repeated 3 times so far. What do you expect to see? You have a circle here. What do you expect to see afterwards? A potato, yes, correct. So first potato, this is a very squished one. So why is what's happened here? What's happened in the y direction? All right, so how is this matrix? It's a cute matrix? It's a rotation matrix? It's an annoying matrix?
It is a 3x2 matrix.
How are what are the singular values? Look here. One singular value is almost close to 0, right? So this is an almost singular matrix. So this is what's happening. It's going to kill one dimension. This one didn't kill it yet. But basically you have that the dimensions in the diagonal, right, in the singular value of decomposition, represent the amount of zooming you have in the different direction. And then the first 2 matrices, the first and the last one, represent the rotation that these metrics apply. This other one has a factor of 2 in one direction and the 0.6 in the other one. So you get this stuff here. Oh, something else. Hold on. So here you have blue, green, yellow, red, right? So RG, hold on. No, there is no order here. Okay, blue, green, yellow, red. And then here you have blue, red, yellow, green. So what's happened here? How is the determinant? Negative. Why is that? Because you had a reflection. That's correct. All right. Keep going. You can see here different things, right? So you have more potatoes here. And this is actually zooming a lot. You have 1.3. This also is kind of zooming a little. Okay. This one does nothing. Okay. Boring. Right? Oh! Okay. What's happened here? How is this matrix? It's going to be singular, right? Almost. You can see the one singular value is going to be 0.03. It's very tiny. You can see these are the unit vectors. There are very big arrows here. Means it has squashed down, right? The first one is 0.6. The other one is 0.03. So you can basically you almost kill a dimension here, and so on. Okay, so not much stuff. Anyhow, you can do the same things with PyTorch now. So this is going to be the first instruction you're going to be seeing about PyTorch. So here I do model. It's going to be a sequential, which is basically a container where I can put a few modules one after each other. And my first module is going to be a NN linear, which means, what does NN linear means? Doesn't mean a linear transformation, because these people were, I guess, programmers. So, they don't know, I guess. This is an affine transformation. But actually, it's a linear transformation because I set bias equals false, okay? So this is actually just a matrix multiplication. So it is a linear transformation, okay? Maps 0 to 0. Then I do model to device. So I ship the model to the memory of the GPU. And then I remove the gradients. You're going to figure out this next week, what it is. I'm going to get here my y is going to be the output of the model, to which I input the x. Then I generate my figure and I plot this stuff. So this is to show you that you can also get a singular matrix with the PyTorch. How cool is this? No, it's boring, right? I mean, you can see you can multiply data by matrices by using the PyTorch package. And so we had to create a model, a sequential container. We put inside the linear module. We remove the bias, the translation, and you get this stuff. Why did I remove the translation? Because otherwise I had to fetch it and it goes outside the screen, so I keep it in the center. Okay? All right. So, let's have this one. So right now I'm going to just use the following. I just use a matrix that is, I think, identical. No, it's going to be an identity matrix, which I scale both items in the diagonal by the same item, by the same value. And then I apply a non-linear function. So my non-linear function is going to be the following. It's a hyperbolic tangent. which goes to -1 roughly when you cross the -2.5 here on the bottom, and it goes to 1 roughly whenever you cross the +2.5, okay, up here. So this stuff maps what? The whole real line to where? So plus infinity goes to 1, and minus infinity goes to until you reach the linear region, which is roughly -2.5 to 2.5. Why do I mention these numbers? Because sometimes you're going to put your nose inside your model that is not training, and you still want to figure out the order of magnitude and the number which are kind of associated to the kink of these nonlinearities. Anyhow, so I just create this one, which is very, very similar to the thing I just showed you before, which has, where is it? Here. So here I have my sequential, which is this sequence of operations. I use a matrix first, so this linear to 2, and then I apply the tan h. And then I increase the, I think, the multiplier for that diagonal matrix. So that's what you get. So this is my cloud. What do you expect to see of my cloud? So what is the range of this cloud? We said it's roughly? It goes from -3 to +3, right? Where is the kink happening? So everything that is outside this 2.5, -2.5 to +2.5 box is going to be mapped to 1. Things that are inside stay roughly the same. That's correct. So what do you expect to see after this image over here? You expect to have in box your data, but what is going to be the size of this box? Are you sure? So the suggestion was from -2.5 to 2.5. The box is going to be to -1 to +1, so -1, -1, I mean all the box from -1 to +1. But then the points inside are going to be mapped according to the mapping we were mentioning before. So things from -2.5 to 2.5 are getting linearly squeezed, and then things outside the 2.5 number are going to be squashed down to the basically edge of this box. Okay? Are you ready to see how to box a normal distribution? Are you excited? Okay, just 2 people just said that. I mean, are you excited? Come on, give me some satisfaction. Okay, you're not playing with me. Okay, I see. I'm trying to be nice to you. Oh, thank you. At least that worked. All right, so that was first one. So in this case here, I just show you just my identity metrics. I didn't zoom anything. And here things are kind of, what kind of distribution looks this? I mean, what does it look like? Come on.
Uniform.
Oh, it's a uniform, kind of, between -1 to +1. Fantastic, in 2D. What does it happen now if I start zooming a little bit? If I start multiplying, instead of having an identity matrix, now I have the 2-2 matrix, or 3-3, or 4-4, 5-5. Say again? The points will go further to the edges. So you're going to be seeing this, and this, and this, and finally this one. Oh, eh? Cool, no? So what happens here? We mapped our cloud that was like circular into this kind of boxy thing. How cool is that? Now those little points are very, very spread apart. And so you can actually tell them apart if you are, for example, classifying stuff. Finally, in the last minute, then I let you go. Is going to be using random matrices, but in this way. So here I'm going to have my sequential. I put like a linear layer, which also has the bias term, so it's a fine transformation. I go from 2 to this hidden layer dimension, which is going to be 5. So I go to 2 to 5. I apply the ReLU, which is simply the positive part operator. And then I apply another affine transformation that goes to 5 to 2. Such that I can display them on the screen, okay? Is it clear what I'm doing? So I create a sequential, which is a sequence of modules. I have 3 modules. The first module is a matrix mapping matrix of height 5, width 2. So it shoots towards 5 dimensions from a two-dimensional input space. There is a bias, which is going to be 5-dimensional. Then you set to 0 everything that is negative, and then you map this 5-dimensional space, whatever, down to 2 dimensions. So you're going to have a matrix that has 2 rows and 5 columns. And then there is a bias of height, like of size 2. Okay? Did you follow? If you didn't follow, you can find in the recording. Because I'm going to press play. Are you ready? Yes. Okay. Some engagement. Okay, it didn't work, sorry. Okay, okay, fantastic, now it did. So this is the beginning, right? That's the starting point. And then you get, yes, you're allowed to do, it's fine to, this is right? This is very spiky. So you're gonna figure out in the next class what happened here. This is a very different thing, right? These are smooth transformations. Somehow smooth. This is very, very angular, right? And this one. And how cute is this, right? So finally, final remarks, and then I'll let you go. I know it's dinner time. Sorry for keeping you here 2 minutes late. So final remarks are the following. Then, check the piazza. So this is basically a untrained neural network. Those I just showed you in the module with the 3 items, the linear transformation, the positive part, linear transformation, or affine transformation, is your first linear deep neural network. It's not that deep, but still makes pretty damn awesome drawings, I think, in my opinion. So unlike a just initialized network, an untrained network will start with this kind of transformation. But we have seen from the first video I show you tonight that we are aiming for a transformation which is, instrumental to perform a specific task, which is, for example, the classification of those points that are belonging to the different 5 spiral. So in the next class, we're going to figure out how do I take this initial, arbitrary transformation, and I can pull it apart and manipulate such that I achieve the final goal, which is, for example, make my points linearly separable in the final layer. Okay? So this is going to be for the next class. Otherwise, stay warm, and I see you next time. Bye-bye.